Welcome to Further Solutions Academy. Please, this is Further Solutions Academy. Please do well to share and subscribe. Subscribe to our YouTube channel, and also you can reach us on you can comment and reach us on +234 80344 95990. So you can reach us on WhatsApp, you can reach us on Telegram, you can even give us a call for topics that are challenging and you need help with them. You can reach us on this contact. So please don't forget to press the subscribe button as you follow us through this lecture. For today, we'll be exploring an aspect of physical chemistry, which is chemical equilibrium. And the aspect of chemical equilibrium we'll be exploring is equilibrium constant in equilibrium reactions. Equilibrium constant in equilibrium reactions. Equilibrium constants in equilibrium reaction. So for us to do this, we'll be taking an hypothetical equilibrium reaction where we have A moles, of A reacting with B moles of B to produce products of C moles of C and D moles of D. This is just an hypothetical equation, and this hypothetical equation could be written in this form. Don't forget the reversible sign. We are talking about equilibrium. Sorry for that. Where A, B, C, and D, the small in the lower case, are the number of moles. For this concept to work well, we'll be using the law of mass action. We'll be using the law of mass action, and the law of mass action states that the law of mass action states that the rate of the reaction is directly proportional to the active masses of the reactant species of the reaction is directly proportional to the active masses of the reacting species. So the law of mass action once again states that the rate of a reaction is directly proportional to the active masses of the reacting species. So this will bring us to the aspect that what exactly are the active masses? The active masses are actually the concentration of a substance or the species raised to the power of the number of moles as represented in the chemical equation, the balanced chemical equation. That is what active masses are. Active masses are the concentration of the species raised to the power of the number of moles as represented in the balanced chemical equation. So for this hypothetical equation, like I said, we are using the law of mass action with the active masses. So we'll be using this equation to derive our equilibrium constant. So this class will be deriving. Perhaps by next class we would go into answering a question with this. So we have our equation once again to be a plus b to give us c plus d, where a, b, c, d are the number of moles. So we have two different equations. We have the forward and we have the backward. So for this hypothetical equation, the rate of the forward reaction that is Rf, represented as Rf, is directly proportional, using the law of mass action, directly proportional to the active masses. And we say active masses is the concentration of the species raised to the power of the number of moles as represented in the balanced chemical equation. So this is the rate of the forward reaction for this species. And if we are going to remove the proportionality sign, that means we are introducing a constant, which means the rate of the forward reaction is equals to the rate constant of the forward reaction. Please take note that they are written in concentration is being written in square bracket. Please take note they are being written in square bracket. So this, where we say Kf is what? The rate constant for the forward reaction. The rate constant for the forward reaction. This is the forward reaction. And remember, from your rate law says that your rate is directly proportional to the reactant, concentration of reactant. So if this is the forward reaction, this is the active reactant at that point in time. So for the backward reaction, the rate of the backward reaction will be having this way, where this becomes our reactant, because it is a reversible equation. So we have this to be this to the active masses. Then to remove the proportionality constant, we have Rb is equals to Kb with our concentration all over again to this. And where Kb is equals to what? The rate constant of backward reaction. The rate constant of backward reaction. Now, at equilibrium, what we realize is that the rate of the forward reaction is equal to the rate of the backward reaction, where we have Rf is equals to Rb at equilibrium, because there must be a balancing. And as a result of this, can we substitute the value for our Rf and the value of our Rb into the equation and see what we have? So that means if we do this well, we'll be having something of this sort, where we have our Kf A B is equals to Kb C and D. So we want to equate both of them together to give us to have a unitary rate constant for both of them. If we do the mathematical sign of this, we realize that we end up having Kf over Kb is equals to concentration of C raised to power of number of moles D over A and B. This is what we'll be having if we do our mathematics well from there. Then it is realized that this need to have a uniform value. So we say Kf over Kb is equals to Kc, where Kc is our rate constant, equilibrium rate constant. So our Kc is the equilibrium rate constant. So it could be said that Kc is equals to concentration of C and concentration of D over concentration of A and concentration of B. So this, we have derived the equilibrium rate constant from an hypothetical equation. Now, there are different significance of Kc. When your Kc is large, then it means that you have more on the product side. You know, we have substituted Kc for Kf and Kb, but nevertheless, we can still use it to say something about the equation. When the Kc is large, it means that we have more on the product side, and that is when Kc is large, it means that we have more on the product side, and when Kc is small, it means that we have more on the reactant side from the balance equation, the reactant and the product. Whether we are not saying whether it is forward or backward right now, but this is what the indication that we get using our Kc. The next thing we'll be doing is we would have just to show that we understand what we are doing. Let's just have an example of an equation where you just give the equilibrium constant. Quite simple, but let's do it. Let's say we have 3 moles of hydrogen gas reacting with nitrogen gas to give 2 moles of ammonia. 2 moles of ammonia gas. Okay, sorry. This is an equilibrium reaction. So how do we put this in equilibrium constant? We have Kc should be what? So we have NH3. Please don't forget your square bracket. Raised to the power of 2 over H2 raised to the power of 3 and N2. So this is how to present our equilibrium constant. Please note that when you are presenting your equilibrium constant for your equations, when you have a solid or liquid, the equilibrium constants are constant, so they don't show in the equations. We'll be dealing with this when we get to the concept of ionic equilibrium, but before we get there, let's just finish with this. So this is an example of an equation. So the next thing we'll be talking about, we'll be deriving an equation or that shows the relationship between equilibrium constants Kc and Kp. You must have seen this before in some textbooks where you are using Kp, and you must have seen some where you are using Kc. There is a relationship that exists between them, and this relationship is derived from a formula that we will be going into right now. Let's still take our hypothetical equation of where we have A plus B to give C plus D. All right. Let's assume they are all in the gaseous state. Let's assume, because this Kp is talking about gases and pressure most especially. So since we have this, then we know that our Kc for this equation is equals to, oh sorry, this is a mistake, sorry. So this is we have C D over A and B. Please note that we have a multiplication symbol between each of them rather. So since concentration is directly proportional to partial pressure, Since concentration is directly proportional to partial pressure from our relationship of concentration and pressure, we realize that, so like I said, our concentration is directly proportional to our partial pressure. So we'll be expressing them in form of partial pressure, where we have Kp as a proportionality constant for pressure to be Pc raised to the power of C, and I'm not using square bracket because I'm not talking of concentration now. P D raised to the power of D over P of A raised to the power of A, and P of B raised to the power of B, at where PA, PB, PC, and PD are the partial pressures of A, B, C, and D. Okay, I think I should write that out. PA, PB, PC, and PD A, B, C, and D respectively. So, having known this, then I think the derivation process has just started. From our ideal gas equation, we realize that we say PV is equals to nRT, right? Where N is the number of moles and R is our gas constant, where N equals number of moles and R is our molar gas constant, where I hope you are aware that R has different units. Molar gas constant. So from our ideal gas equation, we could realize that P is equals to nRT over V, or NV over RT. N over V over RT. Now, this is from our ideal gas equation. Please remember that concentration is the number of moles. When you say concentration, it's number of moles, the ratio of number of moles to volume. Where concentration, let me bring this up. I hope we are following. Where concentration is N over V, that is the ratio of the number of moles to the volume of whatever you are using, you are observing the concentration. So we can as well say, since our concentration is this, we could substitute the value for our concentration of each of these species for this position here. So what we are going to have in other way is, when we have for PA, we will be having concentration of A. Substituting this in terms of concentration of A raised to power of A, then RT of A for the partial pressure. Now we want to use the ideal gas equation to relate it to the partial pressure. Then for PB, we are having B RT B. Then for PC, we have C, concentration of C, RT C. Then for PD, we have D, RT D. The reason what we are just trying to do is to substitute for the place of P. Now, this is just P. So when we say we are using PA, we substituted the place for the concentration, and we are just imputing all of this entity into what we had earlier on to represent our partial pressure. Remember, earlier on we had something like this, something of this sort, where we say our PA is equals to P of A raised to power A, where we had something like this in using the Kp expression. So we are just substituting, and we have all of this. So having known this, we are going to substitute all of these values into our Kp. We are going to substitute all of those values into our Kp. Remember, our Kp once again is P of C, P of D, over P of A raised to power of A, and P of B raised to power of B. So we are substituting all of this into this equation. So our Kp automatically becomes, since we are starting with C, we have C RT C, right, D D RT D over A RT A B B RT B. So we are going to collect like terms here. We'll be having our KP to be equals to CD, right? CD RT. From the laws of indices, when we have the same basis, what do? We add the power. We have the multiplication sign also. Multiplication sign also, which is I think the first or second law of indices. So that becomes C plus D over A, concentration of A with concentration of B. Then RT comes together. That is A plus B. I believe we still remember this from our laws of indices. So automatically we have collected the like terms together in expression with relation to our KP. So there is still something that can be done here. If you would agree with me, you realize that all of this entity is our KC. All of this entity is our KC. So what we are saying is KP becomes equals to KC because all of this represent KC. So KC, hold on, KC, then we have RT. Now from our laws of indices also, realize that when we have powers, when we have the same basis and we have a division sign, there's a subtraction that comes in place. So we say this is C plus D minus, because of the division sign, A plus B. So this is the expression we are getting from this. Having this expression, you realize that from our basic mathematics, we could actually expand, or we can expand this and we could leave it like that. But I would like to bring this out already. So let's just say we have C plus D minus A plus B. This, because we want to make the equation quite easy to understand, we will be representing it with delta N, change in the number of moles. Remember, this small a, b, c, d are the number of moles from your balanced chemical equation. So this will be represented as delta N. So I can say, in other words, that my Kp is equals to Kc RT delta N. So this is a relationship, but we may not stop here. But in a situation where we have delta N to be giving us 0, delta N to be giving us 0, it means our Kp is equals to Kc RT raised to power of 0. And from our basic mathematics, you realize that anything raised to power 0 is 1, at least for the basic level sake. So if that is that, then this becomes 1. Then we have our Kp should be equals to what? Kc. And this is what shows the relationship between the equilibrium constant for pressure and equilibrium constant of concentration all together. And how we got this is the derivation we have done so far. In our next class, we will be having questions or problems that we'll be solving with respect to this particular concept. Please do well to check our next video and follow us so you can be updated and see examples on how this that we have derived could be used to solve a problem. So please, once again, this is Further Solutions Academy. Please do well to share and subscribe to our YouTube channel, and you can reach us on +234 80344 95990. You can either call us or you can reach us on WhatsApp or even on Telegram social media. Whenever you need, you could drop a comment on our YouTube page. You could give us a direct comment or contribution or anything that you would like to know. And please, you can reach us on this contact and we will be glad to attend to you or to offer our services. Once again, thank you very much.